So what I'm noticing as we get further and further into chapter 12 is that it has it's the same kind of problems, but they just have slightly different vocabulary they're using. So in our last section, we talked about probability of unions and intersections of two events. And basically, with unions and intersections, P of A and B, or P of A or B, it was like combining two events into one event. And with like when they ask what's the chance of drawing a queen in one card, and then you say, okay, that's probability of A, we'll call that queen, is 1 out of 13. And say the probability of drawing a 6 with another card, well, that's also 1 out of 13. So then when we say, what's the probability of drawing a queen and a 6 with one card? But it's not, we're still talking about that one draw, so we're not changing the amount of cards we're drawing. So then that's asking what's the overlap, and we're still thinking, okay, we're 52 cards. But it's not like I multiply or anything, because I'm not drawing two cards. I'm still drawing one card. So P, A, and B, which we did was the last section, does not add to the number of draws, and neither does P, A, or B. We're still talking about one card, P, A, or B. Well, I'm going to add these two together, and there's no overlap. There's no queens that are also 6s. So it's 2 out of 13. And the probability of drawing a queen and an A and B in one card, I draw a queen and a 6 at the same time. That's 0. So this is P, A, or B, and P, A, and B here will be 0. Now, section 12.5, well, now we're talking independent events, two events. So now we're getting back to what we were looking at with the counting principle, with the probabilities, with the tile problem that we talked about in class. So let's try some. So I'm going to do some even problems, and hopefully you can catch me making a mistake. So this is page 734, number 24. We're playing a game that involves drawing 3 numbers from a hat. There are 25 pieces of paper labeled 1 to 25 in the hat. So I'm drawing 3 numbers. Each number is replaced after it is drawn with replacement. So again, with replacement versus without replacement, right? If it was without replacement, I would be like 25 the first time, 24 the second time, 23 the third time. But we're replacing, so it's always out of 25. Okay. What's the probability that each number is greater than 20 or less than 4? Greater than 20, so that's 21, that's 5. Greater than 20, the chances are 1/5. Or less than 4. Well, less than 4, that's 1, 2, or 3. So that's 3 25ths. I guess I'll convert this 1/5 to 5 25ths. And the chances of it being one or the other on each turn will be 8 25ths. The first time, and the second time, and the third time. So I believe the chance of each number being greater than 20 and less than 4 is going to be 8 25ths to the third power. So let's see what that is. 8 25ths to the third. So 3.3% is my answer. 3.3%. All right, approximately. All right, 26. Next problem we'll try is trading cards. So you're collecting movie trading cards which have different scenes from a movie. For one movie, there are 90 cards, and you have all of them except the final scene. One movie, there are 90 cards. All right. To try and get this card, you buy 10 packs of 8 cards. So 80 cards. All cards in a pack are different, and each of the cards is equally likely to be in a given pack. So we're on page 735 now, number 26. So find the probability that you will get the final scene. So we're trying to get one card out of 90, and we're buying 80 cards. Now, if this were easy, if this were 7th grade, it would just be 80 out of 90, and we'd call it a day. But we know it's not that easy, right? So again, the problem states it's a 90 card set. I want one, and I buy 80 cards. I buy 10 packs of cards. Each of them has 8 cards in it, all in an attempt to get this one card. And so you would think, well, if on my first try, if I look at one card, I'd have a 1 in 90 chance. But then I do that 80 times. But then, and so in that 8 card pack, I'd have an 8 out of 90 chance. But we actually have a better, more precise way of looking at what our chances are of getting that card. So in one pack, the probability of, let's look at the probability of not getting the card. Okay, the probability of not getting the card, there's 89 cards that are not our card, right? So there's 89, it would be 89 times 88 times 87, all the way down. We're doing 8 cards, so 9, 8, 7, 6, 5, 4, 3, like 82. Or in other words, 89, now C, 8. And then the total possibilities, period, are 90 C8. So this fraction here is my chances of not getting the card in a single deck. And we're going to replay that 8 times. So that fraction, we're going to raise that to the 8th or to the 10th power because we're buying 10 packs of cards. That exponent is the chances of not getting the card. So to find the actual chances of getting the card, we need to find the complement of that. So it's 1 minus that fraction to the 10th power. And if I want to look at that, what that fraction looks like, really, I've got 90 times 89 times 88, to 83, right? Because it's 8. So a lot of stuff cancels here. These are all going to cancel. The 90 stays and the 82 stays. So it is 82 out of 90 is my chances of not getting it. And so that's what we would have thought in the first place. 82 out of 90 would be our chances of not getting it. So using this, we get 82 out of 90 is our chances of not getting it. Now, 8 out of 90 is our chance of getting it. And we're thinking, well, if you try it twice, you could raise that to a power, but that gives me a smaller chance. I want my chances to increase. So what I'm going to do is look at the chances of not getting it and raise that to a power. And I'll raise it to the 10th power because that's how many packs I got. 82 to 90 to the 10th power is 0.394. So that's my chances of not getting it. The complement of that will be my chances of getting it. So that's going to be about 61%. 1 minus this equals 60.6%. All right, we'll talk about it more tomorrow in class. Good night.